If you have ever observed the flow of water from a tap, you may have noticed that at some times the flow is very smooth. The water is almost transparent even though it is flowing, and it seems that the flow of water is very orderly. And as the water gets farther and farther away from the tap as it falls, that flow gets disturbed, the water becomes cloudy and roiling and turbulent. So that smooth flow of water, or for any fluid, is what we know as streamline flow. Let's try to understand this phenomenon from the standpoint of physics and why it is important in the study of fluids in motion. So streamline flow is a very specific type of flow in which all the water molecules are following certain common behaviors. So let's understand what that behavior is. Let's say that you are observing the flow of water through a pipe. So here we have a pipe, and we have water flowing in this pipe in a single direction. Let's say that you are assigning velocities to the various particles of water or the water molecules as they are moving from one end to the other. So the water molecules at this location, let's say we circle this location, let's call this location A, have some velocity, let's call it VA. And the water molecules at this location, let's call this B, have some velocity VB. And here is another location C, let's call this location, let's call this velocity VC. So let's try to understand a simplified example of streamline flow. Let's say that we are studying the motion or the flow of water in a pipe. So here we have a cylindrical pipe, and we are representing the motion of water through this pipe in the form of these lines. So the water is flowing from one end to the other. Let's say that we pick 3 random locations in this pipe. Let's say that we have a location P, we have a location Q, and we have a location R. Now let's say that we have a method by which we can measure the velocity of the water particle as it is passing through these points. So at time t equal to t1, let's say, you are measuring the velocities of the water particles as they are passing through the points P, Q and R. So at that moment, if you take the velocity of the particles passing through point P, that velocity is Vp, and at the same time for Q, that velocity is Vq, and for R, that velocity is Vr. If the flow of this water is in streamline flow, if it is a streamline flow, we notice that these velocities for these particular points will always remain constant. The flow velocities may be different, Vp, Vq and Vr may be different from each other, but for that location in the pipe, the speed or velocity of the water flowing through that location at any given time will remain the same. In other words, if I were to construct a map which shows the velocity of water particles at any given point in this pipe, that velocity map would not change with time. Let's try a slightly more complicated example to understand what is happening here. Let's say that we have a differently shaped pipe such that its cross section is not constant. So here we have a pipe whose cross section is changing. Let's again define 3 points. Here we have point P, here we have point Q, and here we have point R. We can also associate a cross-sectional area with each of these points. So I can say that this point P is associated with a cross-section, so is point Q, and so is point R. So this cross-sectional area, the cross-section of the pipe through which the water is flowing, let's call this A subscript P, here it is A subscript Q, and here it is A subscript R. If we were to look at the flow of water through this pipe with varying cross-section, and if this was a streamline flow, we would see a pattern that looked something like this. This would be the pattern that we observe for the water as it flowed through the pipe. And this pattern would remain constant with time. What does that mean? It means that if you were to look at the velocity of water flowing through the cross section AP, let's call this Vp, and compare that with the velocity of the water as it is passing through AQ, that is VQ, and through AR, that is VR, these velocities may or may not be equal to each other. In other words, as the water is traveling between the points AP, AQ and AR, the velocities could be changing, but the velocities at AP, AQ and AR would always remain the same. In other words, the velocity map for this flow of water would remain constant with time. As the water passed through the point P in the cross-section area AP, its velocity would always be Vp. As it passes through area AQ, it would always be Vq. As it passed through area AR, it would always remain VR. This pattern would not change no matter how long this flow continued. So, for a streamline flow, each of these particles passing through these lines will be like trains, like the compartments in a train, which are always traveling at certain velocities through certain points. So, each molecule or each particle of water seems to be traveling right behind the next molecule. These lines or these streamlines will not intersect each other. And if they did intersect each other, the water particle would have to follow any one streamline. It cannot simultaneously belong to two of them. Now, mathematically, we can understand what is going on here by studying how the mass of the fluid flows through this cross section. So, let's study how much mass of water is passing through the cross section A subscript P. This can be given as AM subscript P, that is equal to rho P times A subscript P times V subscript P multiplied by the time interval of interest, that is AT. Here rho is the density of the fluid, A sub P is the cross-sectional area of that region where the water is flowing or the fluid is flowing, and Vp is the velocity of the water particles as they are crossing that cross-sectional area AP. In the same way, we can also calculate the mass of water that is passing the surface or the area AQ at any given time or in any given time interval. That is given as A m subscript q is equal to rho q times AQ times V sub q times the time interval of interest AT, and so on. We can also do this for the cross section AR. So, here it will be A mr is equal to rho r, A sub r times VR times AT, that is the time interval of interest. We will notice that as the water is flowing through all of these three cross sections, if the water is not compressible, right, for normal pressures we consider water to be an incompressible fluid. In that particular case, we will say that the density of the fluid at any of these points, that is rho p is equal to rho q is equal to rho r. In other words, as the water is traveling through this system, the density remains constant. Now, in this particular case, we can understand intuitively that if the density remains constant, there is no compression or expansion of the water, there is no change in density of the water or the fluid as it is moving through the system. That means that the same mass is crossing any given area at any given time. In other words, the amount of mass that is passing through the cross section AP will be the same as the amount of mass passing through cross section AQ and through cross section AR. This means that as the cross sectional area of this pipe is increasing, the velocity has to decrease because the mass has to remain constant as a function of time. Conversely, if the cross section of the pipe is decreasing, the flow speed has to increase in order to make up for the smaller cross section area, because you have to get the same amount of mass in the same amount of time through that smaller cross section area. You can only do that if the flow speed is increasing. Based on all this, we can say that since we are dealing with an incompressible fluid and the same mass of the fluid is transiting through any of these cross section areas for any given amount of time, we can come to the conclusion that AP times VP is equal to AR times VR is equal to AQ times VQ. And this is what we call the equation of continuity, which is a characteristic of a streamline flow. So the question might arise, where does this equation of continuity stop having meaning? We are assuming that the flow is streamline. In other words, each successive molecule or each successive particle of water is tracing the same path as the previous one and the one before that. In real life, streamline flows are very difficult to maintain. There are inherent properties inside the fluid medium itself. There is friction and there are other effects which cause the streamline to break up and the flow to become much more irregular. This irregular flow is what we call turbulent flow or turbulence, and that is what you see in the tap. Once the water has passed through a certain distance, the flow starts becoming disorderly and turbulent, and the continuity equation fails to be valid for a turbulent flow of fluid. So let's summarize what we have learned so far.
Manorama Horizon. Learning made simple.